Okay, so today we're going to find the area underneath the curve. Oh my gosh, we're almost out of time. Okay, area, not in the right pen color. So area under a curve. And this is just a fancy, easy way of a geometric way of looking at it. If I give you a curve, let's call this, so do something like this, okay? And we call this f of x from, let's say, A to B, right? If I take the integral, it will literally give me the cumulative change. Cumulative change. Okay, cumulative means adding up, and adding up all the changing values. Y, 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 y. We did this simply using Riemann sums, where we drew little rectangles, right? And this was an approximation. And we said the more rectangles I draw, the more accurate this approximation becomes. And if I can draw an infinitely many set of rectangles, this becomes the actual area underneath that curve. Now, why is finding the area underneath the curve so difficult? It's because it's a curve. It's like trying to fit a square inside a circle. You can't do it. Well, you can fit it, but it doesn't cover enough space, right? So we can't fit square things or, polygons into circles, curved shapes. So what we do is we have this idea of the integral from a to b of f of x dx, and this gives us our area. Now, that's the crazy part. Why does this give us our area? Okay. Well, if you look at this integral symbol, this looks like an S, doesn't it? For sum means adding it up. And we are adding, what are we adding? We are adding actual y's, which are our heights, times our x, which is our base. And a height times a base gives us the idea of area. Now, what dx is? We said dx is a little x. How little? Little as in goes to infinity, small, right? Or sorry, not infinity. I meant 1 over infinity, goes to 0, right? The idea here is that this x is so small, it is a small, fine sliver. And if you take a small, fine sliver times the y value, that gives you a small, tiny line. Sorry, people are coming in. So if I add up all my little fine lines, let me draw this a little differently over here. If I take my f of x, right, and I multiply by a little bit of dx, that'll give me one fine line. And then I take the next f of x, and then I add it, and I add them together. And I keep doing this over and over and over, repeatedly. You get the idea. It will end up forming the stupid curve that we're expected to cover from A to B. Right, that's the idea here. And the sum adds up all the areas. So we're summing our areas to become the total area. Okay. So when you look at the integral idea, you must be aware that that's just a y value times a little bit of x, which is just really an area, a very small sliver of area, and we're going to add up all the areas from A to B. Now, a couple things may happen is what happens if your graph looks like this from A to B, right? Well, I want you guys to notice that the y values here are negative, and the y values on the right side here are positive. So here is a trick I'm going to have you guys do right now. On your calculators, please write the integral from 0 to 2 pi of, let's do sine of x dx. Okay, sine of x dx graph looks like this. Okay, to 2 pi. And you guys are going to add up all the y values, right, times a little bit of dx, all the slivers along the way. Now you can see this is a positive, and this part's negative. And a sine graph is totally balanced, nicely equaled out. So on your calculator, please go ahead and practice typing this in your calculator. Now, if you guys have the non-pretty font version, you are going to type this. You're going to say sine x. So it's going to give you in. Let me see what this is. I forgot what it says. When you guys hit Math 9 on your non-pretty version, it'll say fn function integration, and then you'll type sine x, comma 0, comma 2 pi, comma x. So this is what you would type if you guys didn't have pretty font. This is for a TI, whatever. TI like 83 or even 89 has pretty font.
Is it for an 84?
84, you would probably. Does the 84 do that pretty font? It doesn't.
I don't. What's pretty font?
Pretty font makes. Remember how when I was showing my calculator, it looked all nice. Let me go ahead and share my calculator again.
Oh, like it gave you the integral sign?
Yeah, it gave me the integral sign itself.
Yeah, I can do that.
Oh yeah, then forget it. It's not yours.
So I can just type in the normal integral for this,
Yeah.
right?
Yep. Just do the Math 9. Okay. Anyone get an answer?
I got 0.
0. Perfect. That's 0.
I don't have to put anything at the beginning, right?
No, this isn't the average. This isn't the mean.
Oh, so this you just find the integral.
Right. I just want to
Between
find
the
out what
two
the cumulative
spaces.
change. And hopefully
Okay.
you guys are getting 0 here. Now, I want you guys to change one thing for the calculator. Go ahead and hit up and enter again, and it'll copy the entry. If not, on your calculator, you have a nice entry button. You guys see on the lower right hand corner, it's in blue, it says entry. You can go second entry and it'll repeat again. I want you guys to do this. Right, next step, please do the integral from 0 to pi only of sine x dx. And see what answer that gives you. And then you're going to do one more for me. You're going to give me what's the integral from pi to 2 pi of sine x dx. Okay? So go ahead and do those things. I want to show you guys, like, why is it 0? And does it make sense that it would be 0? If you guys don't know where the pi button is, it's going to be right underneath the clear. Sine x dx. Okay, you guys should be getting the number 2 here. Anyone get 2? Oh, make sure you are in radians.
I got 2.
Good, perfect. Make sure you are in radian mode. If you're not in radian mode, if you're not in radian mode, you have to change modes. So on the upper keys where it says second mode, hit mode. And you want to make sure you are in radian mode, not in degree mode. That's like the 4th option down. Oh, that's for the TIs. Okay, if you're not getting 0 or 2, make sure you are in radian mode. And then from pi to 2 pi, you should be getting -2. So if I told you the area for this part was +2, and this here was -2, well, 2 minus 2 is 0. Okay, you guys are following along? You guys are okay with this? So you can see why it's 0 is because cumulative change means I'm adding up all the parts. So you can think of this as a story of making money. I'm making money here. I'm making money. Oh yes, look at my bank account. Super big. Yeah, making money. Oh, I'm making less money, but I'm still making money. Okay, I made $2. Good job, Mr. Ko. And then if I keep counting, I'm going to start minusing from my savings. I'm adding negative value. That means I'm losing money, and then we're back to 0. Okay, to show you that this idea works of area underneath the curve. Okay, now this works for all types of functions. Any function you plug in, the integral we'll find that total area, the cumulative change. Now here is a different story though, okay? What if I asked you guys to find out, we can use this as a different way of looking at things. I'm going to change this idea here. And what if I say f of x of sine of x is distance traveled. Okay, distance traveled. Well, actually, no, not distance traveled. This is, I want to find distance traveled. I want to find distance traveled. Okay. So I want you guys to take a look at this. Imagine this was the equation of the location. F of x is a position. Okay. At sine of 0, my position is 0. Okay. And as the graph goes to pi, I like using this as example of here is, okay, we go up. Actually, no, this is velocity. Darn it, this was the wrong thing. This is velocity. Velocity. Okay, sorry, change it to velocity. So think of this as me on a bike and velocity. So I have positive velocity means I'm going forward. Going forward. And then if I have negative velocity, what do you think? I'm going backwards. So if I go forward 2 miles and I go backwards exactly the same 2 miles, where am I back? I'm back to where I started from. So if I start at my house, I go a total distance of 2 miles away, and then I ride backwards on my bike a total of negative 2 miles away, I'm back to where I started from. But what if I wanted to find out how far I traveled in general? What is the distance traveled? Me riding forward and me riding back, if I go forward 2 miles and I go back 2 miles, didn't we go a total of 4 miles? Right? That's this idea. And now that's the hard question. Am I asking you where we're at position-wise, right? I went 2 miles and I came back 2 miles. What position are you at? Or are you looking at distance traveled? And this is something that we're going to talk about a little bit later, but we're going to use this idea of area underneath the curve to solve for that. And to find this one, the trick is this. We write an absolute value, the integral from 0 to 2 pi, and we're going to do an absolute value of sine x dx. Now, when you put an absolute value, you turn all the negative values to positive values. So this graph goes, instead of going down, it goes like this, because now it's positive. There's still going to be 2 and still going to be 2, and that's why it adds up to 4. So you're going to see absolute values sometimes, and this is the reason why we use absolute values. Okay, so we'll get into it a little bit later next time, but I just wanted to throw that out there because it always jumps, like, what's the application of this? And the application of this, I can add up values, but what if you want to add up your wins and your losses, right? So, okay, so this is one of the cool things about using an absolute value, using an integral, is that we can find out the area in the curve. We can add all the changes together. Okay. Now, the next thing is we have one more thing we want to cover, and that's the area between two curves. Area between two curves. Now, I'm going to give you guys the most basic example possible. Y is equal to 4 and y is equal to 1 between 0 and 3. Okay? So here's a graph. Y 1, 2, 3, 4. This is the graph for 4. This is the graph for 1. So what is the area between these two curves? What's the area between the two curves? from specifically 0 to 3. So this is 4, this is 1. Now how would we find the area? Well, you would generally go larger minus smaller, right? So looking at these shapes being simple rectangles, what is the area of the bigger shape? So let me just draw this on the side. This is my larger shape. And I'm going to minus, you don't need to draw this part, my smaller shape, right? So what's the area of the bigger shape? The bigger shape is 12 because it's 3 times 4 because it's a stupid rectangle. The area of the smaller rectangle is 3 times 1 is 3. So when we subtract them from each other, 12 minus 3 is 9. So I'm telling you that this is 9. Okay, basic idea, straight from geometry. Now, when we take this to calculus, it's because they're not nice geometric shapes anymore. They're not nice squares or rectangles. What if I switch the top equation with something like y is equal to 2x plus 1? Okay. And the lower equation, y is equal to 1 between 0 and 3. Okay, same idea here. Well, since it's a geometric shape, we could find the area of that triangle. 1/2 base times height between 0 and 3. But if you take a look at here, this is actually, depends how you look at it. People's brains work differently. Some people will say this is a trapezoid. Fine, we can find the area of the trapezoid. We could also instead, we could break it up to a triangle and a rectangle, sure. But we're still minusing the top minus the bottom to find what this overall value is. But let's write this in a calculus way. This would be the integral from 0 to 3 of 2x plus 1 dx minus the integral from 0 to 3 of 1 dx. Okay? Or we can write those together. Since we do have the same a and b, right? Our start and finish value, we could write this together. Hey, this is just from 0 to 3 of 2x plus 1 minus 1 dx. We can write them together. We said if we have a function, if we're taking the integral, we can rewrite integrals. Integral from a to b of f of x plus g of x dx is the same as me writing them separately of f of x g of x, right? And where have we seen this expressed? We've seen this expressed simply by just taking the integral of x squared plus x. We don't take the integral of them together, we do them separately. X cubed over 3 plus x squared over 2, right? We separate them out so our brains don't get too confused. If there's a plus sign, we can separate it. If there's a minus sign, we can separate it. Well, the same thing here. We can always combine it together. So to generalize this, if we have the integral from a to b of f of x dx plus the integral from a to b of g of x, oh, in this case, sorry, we're subtracting them. Well, why don't we just write them together? A to b of f of x minus g of x. And that's exactly what we did here. Now, in this problem, we could simplify it a little bit, right? And just to show you that this would have given us this right answer, I'm going to simplify so you guys don't have to spend a lot of time on your calculators. But 2x plus 1 minus 1, the 1's cancel out, so we have 2x dx. Go ahead and write this in your calculator quickly. Go ahead and write that in your calculator and tell me what the answer is. And I'm going to go and come back here and find out what the area is. Area is 1, 2, 3 by 3, 6 plus 1 is 5, so that's 4. 4 times 3 is 12. 12. The area
I got
is
9 once you put the integral.
yeah, 9 from 0 to 3.
Yeah, 0, 3, parentheses 2x dx.
Oh, that's 7. I'm sorry. Yep. Thank you. 6 times 3 is 18. 1/2. Darn it. I should make this nicer. So if I went ahead and went back to take the area of the triangle. Its area of the triangle is 1/2 base, which was 3 times the height. The height of the triangle was actually turned out to be 6. And that's going to be 9. You guys, you got 9, right? So that's the exact same area as if we went for the triangle version. Now, here is the scrappy part. The part now is that if I give you any function, remember how we said the integrals can deal with curved surfaces? If I call this f of x and g of x, what we can do now is the integral from a to b of top minus bottom. And that's the only rule you have to remember. It's always going to be top minus bottom. And that will give you the area between the two curves. Okay. Now, here is a problem that's kind of ugly, but let me go ahead and give it to you. It's y is equal to negative x squared plus 2x minus 3, and y is equal to negative 2x plus 4. Okay, let's go ahead and graph this on Desmos real quick, and this will be our last example. Negative x squared plus 2x minus 3. And our next graph is negative 2x plus 4. All right, you can see the two graphs here. I want you to find the area that's enclosed between x equals to 0 and x equals to 3. X and 3. If I write that a little differently, comma x and 3. So I'm going to throw up some barriers here. I'm going to throw up like x equals to 0 and then x equals to 3. Okay, I'm going to change, let's do some editing here. We'll call them, make these black, and then also make these dotted. Okay. All right. So we're going to try to deal with the area between these two lines. Real quick, just so you guys can see here, that means I'm trying to shade this area right here. And that's some really weird shape. One's a line and one's a curve. Now, here is the issue. You have to make sure you follow our simple rule of top minus bottom. Top minus bottom. And here's the easiest way I have for you. Whenever you look at the graph, just go top minus bottom. That's it. Just draw a line. Top minus bottom. So we know the top equation has to be the y equals to negative 2x plus 4. And the bottom equation is our negative x squared equation. Okay, top minus bottom. Okay, top minus bottom. So we set it up to find the area. Now, I want you to actually look at this. If I minus this y from this y, doesn't it give me what's left over? And if I multiply by a little bit of dx, that's the area. And if I move over and minus this y from this y, and this y from this y, and this y, and do you really want to do all that work for every and infinitely many set of times? No, but that's what the setup does for us. The integral of negative 2x plus 4 minus negative x squared plus 2x minus 3 dx between 0 and 3. This idea of top minus bottom, if we're looking at graphs going right to left, we would do right minus left because right side's the bigger numerically than the left side. Okay. And you can plug that into a calculator and you're good to go. Now, a couple of things are this. I gave you x squared first, right? So if you had wrote x squared in the front, you would have gotten a negative area because you would have flipped it around. So one big thing is to know that you always want to write the bigger one on top, right? So how do you know which one's the bigger one? One way is just plugging in a value. Pick a number between 0 and 3. Even picking 0 would be easy. If I plug in 0, 0, 0, you see that 4 is bigger than negative 3, right? So you can tell which one is automatically on top. But you sometimes have to plug in a value to figure out what's on top. Or you have to graph it to see where it goes on top. Now there is an issue also, and we'll talk about this next time in class. But what if they intersect? What if I write this new equation here? Let me go ahead and get done with this. Oops. Haha, I didn't even write that down because I erased it. I'm going to give you one more graph here. And this graph goes, let me write it, negative x squared plus 3 and x plus 1. Now, I want you guys to take a look at this graph here. And this graph has an intersection point. If I ask you to find the area between, what value is this over here? That's negative 2. Let's say negative, x equals to negative 2. Darn it. And x equals to 3. Oh, let's do 2. 2 is better. X equals to 2. So if I ask you to find the area, take a look here. Now, I want you to be careful here. This started off as the top, right? But as we continue the graph, doesn't that top become the bottom? And that's when things get mixed up. If I just plug this into my calculator without knowing that the top became the bottom and they switch places on me, you would actually get the wrong answer. Okay, so what happens here is we will talk about this next time, but we'll cut the graph here and we'll call this C, right? So we'll go from the integral from 0 to C plus the integral from C to 2. So we'll have to split our integral eventually. And we'll say this is negative x squared is my top minus x is the bottom, right? Blah, blah, blah. And then we got to flip it, x minus x squared, blah, 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 blah. So we have to spin our equation, and we'll talk more about that next time. And we'll talk about how we can find that intersection point. Okay, and we can do that through our calculator. Okay. All right, so your homework is pretty easy. You guys are just going to be on your calculator this time. We'll come back to talking about how to do these by hand later, but just to make sure you guys can roll them out. First thing, you guys are going to find the area underneath the curve easily by plugging that into a calculator. Second part is you are just going to figure out upper minus lower. You're going to set it up. Just going to set it up. Now the second part you are not going to have to solve. You are just going to set it up. Okay, so figure out which is on top, which is on bottom. Okay, and that's it. Easy peasy homework.